Welcome everyone. In this video we are going to derive an equation for the gravitational potential energy. You might be saying, well, I already know the formula for it. It is mgh. And you will be right in some cases, but this is not the most general formula. And today I will derive the most general formula, and then using that formula we will actually be able to derive this one as well, but that will be the topic of the next day's video. So let's get started. And to make our proof the easiest, I think we need a picture. So here's the picture. We have some celestial body with a huge mass, capital M, and we have a relatively small mass, little m. This is, I would like to think of it as perhaps the Earth, and this is some satellite maybe, okay? So capital M is the Earth and small case m is a satellite, or you can think of it as the moon if you would like. And let's say that there is a distance between them, and when I say the distance, it is the distance between their center of masses, and the distance is called r. Now, Newton's formula tells us that the gravitational force, gravitational attraction between them is as follows. So Fg, and let me write it clearly, Fg is equal to negative g times m times the other m divided by r squared, and this is pointed in the r hat direction. Alright, actually with the negative here, it is in the opposite r hat direction. So for r hat, what is it, you might be asking? It is like this. It is a unit vector, it has magnitude 1, and surprisingly it doesn't have a unit. It is pointed along the radius, basically, along the radial line. And our force is the attraction force, so it is in the opposite direction with that r hat direction. Now, this is the force of gravity that Newton gave us. But today we want to derive a formula for the potential energy, the potential gravitation, the gravitational potential energy, excuse me. So to do that, we will use the definition of potential energy, basically. Now, potential energy is defined as follows. Let's say that you are interested in finding the potential energy at r. This is a vector, your position vector. Then you would need to subtract that, your potential energy. You would need a subtraction, and this r naught is a reference. This is a reference point. So you basically look at the difference relative to a point, because everything is relative in physics and potential energy is no difference. You would need to base your calculations on something, and that something, we name it r naught, and it is called the reference point. Now this is by definition equal to an integral starting from r naught going up to our point of interest r, and it is the integral of your force F times the dot product of dr. dr is a very small infinitesimal length, basically, infinitesimal distance. Alright, and you can perhaps remember this. This is the definition of work, and we just have a negative sign here. You can also think of it like that if you would like. So this is, as I said, by definition correct. And using this for our special case of gravity, we will derive the gravitational potential energy. So let's get started. And by the way, if you don't know what a dot product is, I have a video about it. You can access it from the cards right now. So in our case, and I want to make it in red, in our case we have u r minus u r naught, and we will choose our reference point at the end of our calculations. We have negative r naught and r. Then for the force, we will have this quantity. That's why I talked about Newton's law. We need it. Negative g times m times small case m, r squared and r naught. And if you wonder what the capital G is, it is called the universal gravitation constant. You can find its value on the internet. So this is like that, and we have a dot product. Well, we have this vector dr r hat, dr naught. What am I saying? dr vector. This is the vector, and you can think of it as dr in the r direction. For our case, it could have another It could have another, what do you call? Well, actually, you know what? Let me put the other component as well. You will see that it doesn't matter. Let's say that dr has another component, okay? So it is like dr r hat plus, maybe it has another component which we could call, I don't know, d phi hat. And this means the tangential direction. This is the radial, this is the tangential direction. So if we take their dot product, and if you know how to take a dot product, you basically know that these r hats will cancel because cosine of 0 is 1 and their magnitudes are 1. So these will cancel each other. That is great because at the end we want a scalar quantity. Potential energy is a scalar. It doesn't have a direction. And if you look at this r hat and this phi hat, radial and tangential directions are basically perpendicular to one another. So we have cosine of 90 degrees, which is 0. So this whole term cancels. As I said, in our case, there wasn't that term, but even if we want to include it, it doesn't matter. And you might want to include it for an elliptic case or something like that. But you see that if you include it, if you do the general case, it cancels anyways. So we have R naught, R, and we have negative GMM divided by R squared dr. Here we see that these become positives. Great. So we have some constants here. Remember, these are just constants. And then we have the integral of 1 over r squared dr. I want to write the formula for it. It is, if you have the integral 1 over r, let's write it x, 1 over x squared dx. You take this integral, it is equal to, you increase the power of x by 1, so it becomes 1 over x, and you divide by the new power, so it becomes negative, and you will, let's say that this is x1 and x2, then you will evaluate it at the boundaries. So this is what we have. And this is, well, this is math, basically. This was, up to this point we did physics, and now we are doing the math using a rule of integrals. So we will have GMM divided by R and a negative sign here. And it will be evaluated at these points. You can put the vectors if you want, but it doesn't really matter, and perhaps it is better not to put them at this point because we now have a scalar, no longer a dot product. So you can even avoid them here and here if you would like. Now this will be negative GM divided by R minus, notice that it is important, divided by R naught. Alright, so I want to copy this formula on the new page, and now we will set our reference point. We just derived that the potential energy difference between our reference point and our point of interest is as follows. It is like this, and we have the same term, only difference is we divide by R naught. Now here, think about what the best reference point would be. What would the best reference point be? I mean, could we set it as the, I don't know, as the surface of the earth or surface of our object or something else? I argue that the best reference point is the infinity. I say we should choose R naught as being infinity. And why is that? That's because if we do that, this term will go to 0, because something divided by a huge number, some finite number divided by infinity will give you 0. So it will go and it will make a cancellation. And besides making the formula easier, there is also another practical reason for doing this. Because, for example, when we think about it, it makes sense. What are we saying? We are saying that when I go away from the earth, when I go away enough, when I go to a great distance, the earth's attraction on me, its gravitational pull on me is very, very small that I can neglect it. So it doesn't have any influence on me. That means my potential energy relative to it should be 0. Okay? And you could set it for to be anything else rather than it being infinity. But as I said, this really clarifies a lot of the cases. This is basically the convention. This is how everyone does it, as far as I know it. And it really makes sense when you think of it, because as I said, I want to repeat it, when you go away from the Earth to some distance, of course it will be exerting a force on you, but it will be incredibly small that it is basically neglected. So it doesn't have any influence on you. That means your potential energy relative to it is zero. So we also set this to be zero basically, right? Because if we take it as u of infinity, it is equal to zero. This is our reference frame. Reference frame or point, whatever you call it. So this gives us the final result that the gravitational potential energy at point R is equal to negative g times one mass times the other mass divided by the distance between them. This is the general formula for gravitational potential energy, and as I said in the next video, we will use this to derive the special case of MGH. MGH is correct for only the case where we are relatively close to the surface of the Earth, and you will see what I mean by relatively close. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.